be a bit less soporific just after lunch. I might ask you to raise your hand 1 or 2 times to keep the blood flowing away from the stones as well. All right? And so I'm going to talk a little bit about graph AI and the research that we do at Octavian. So who am I? This is me, Andrew Jefferson. I'm an engineer, my day job, paid a mortgage at EFJ, and I'm a researcher at Octavian. Octavian's an open source AI research team, collective, community, whatever you want to call it. So there's no relationship between these two, apart from the fact that I happen to work at EFJ. Octavian is independent, it does whatever it feels like. So, very quickly, what do we mean by a graph? When I give this presentation in other places, I have to labour this a little bit more. I think we can work through it quickly. When I'm talking about graph today, I'm going to talk about labeled property graphs. The top picture is from the AFJ, and the bottom picture is from DeepMind and Google Brain's recent paper. This is the kind of thing that we spend our time reading in the deep learning, machine learning community. It's a bit less accessible than the top one, but these are basically the same. So we have multiple relationships between nodes. Nodes have properties. Nodes here. Relationships have properties. Relationships have properties. So that's the graph model that we're working with. Why am I interested in graphs? Again, hopefully this audience has an appreciation for the power and utility of graphs. So we can go through this pretty fast. Graphs are everywhere. Raise your hand if you know what this problem is, or who this guy is. Yeah. Go on. No, good guess though. This is the 7 bridges of Königsberg. That's spoiler. But the typhus outbreak in London. Yeah. Would be a good example to use. So yeah, here we've got 4 different flavors of graph. All of them are very useful. So this is why we're interested in graph. My background is from computer vision research, so I'm a kind of trained neural network fanboy, if you will. And I can appreciate that these are really awesome. And I want to bring my cool neural network stuff and I want to use it on graphs. So, what is AI? This is what I want to talk about, and this is hopefully what you're here to find out. This is a trick question. I can't answer this. I've got to use the mic. I can't answer this question. I'd be earning more money if I could. But I'm going to talk a bit about what deep learning is and how we can do it on graphs. So, who recognizes this or has seen this one before? Okay, pretty good. This is our deep neural network. These are densely connected layers. So they're densely connected because every node in the previous layer has some effect on the node in the next layer. And that's the basic building block of neural networks that are used in deep learning. And we call it deep because we have multiple layers. So the depth is width in this picture, but it's that distance there. We've got multiple of these densely connected layers. Right, who knows who this guy is? Someone want to shout out what's happening here? Yeah, he's losing. Yeah, so this is one of the best Go players in the world being beaten at the game of Go by AlphaGo, which is a neural network, basically trained by DeepMind, and it's able to play Go better than the best humans in the world. So we want to bring some of this superhuman AI performance to the world of graphs. Here's some more examples of the stuff that we can do where deep learning, deep neural networks is able to outperform people on pretty complicated seeming tasks. So we've got multiple classification within an image, and we can get 90% accuracy on these kind of tasks. This one I like quite a lot. This is predicting where that car is going to go. Path prediction just from a single still image. And you can see the interfaces here are pretty sophisticated as well. So not just what it's predicting, but the way that the output from the prediction can be something that's pretty useful and pretty intelligible to humans. We're not outputting a matrix, and then the data scientist comes and tells me, oh, we've got 98% accuracy. I take an image and I get out a block of 150 numbers. This is a usable human output. And this is something called MacNet. MacGraph is ours. This is doing reasoning, okay? Reasoning on images from text. So the input question is, what color is the map thing to the right of the sphere in front of the tiny blue block? So you give the network this question and this image, and in multiple steps, it works out how to answer the question. And we can see in this visualization what the network is observing or looking at, if you want to anthropomorphize it, in each step. So it finds, in the first step, the tiny blue block here. In the second step, it finds the sphere. In the third step, it finds the map thing that is in front of it. And the output then is to tell you what color this is. Okay? So this is multi-step reasoning using neural networks. And it's able to outperform humans on these kind of tasks, 98.9% accuracy. I think to some extent outperforming humans is because the humans get bored. If you make them do this task hundreds of times. But it's still pretty phenomenal. So how do we do all of this? Where does it come from? It comes from machine learning. And machine learning has a pretty simple algorithm at the top level. We have some training. We have a model, which is our concept of the world. Okay? These are the neural networks that we're talking about in this case. And then we have a load of data. And to start off with, the model has no priors. We don't program the model to have an understanding of grammar if we're working with text. We don't program the model to have like OpenCV style concepts of edges and spheres and things like that if we're dealing with images. This is pretty much a kind of tabula rasa model, and we're going to learn the weights of that model by training it with data. The outputs from a model are twofold. There are learned weights, so we learn all those parameters that go into the model, and a thing that can do predictions. So sometimes we just use the weights, sometimes we just use the predictive power, sometimes we use both. Okay, let's try and make that a bit more concrete rather than abstract. This linear regression we can put into this concept just to make it a bit clearer. So hopefully most people are familiar with y equals mx plus c linear regression. And in this pattern, the parameters that we learn are m and c. Okay, so to start off with, we're just saying we think the world works like this, and we learn from data these values. And that might be useful, okay? In physics, figuring out what m is from a load of data is pretty important. That's how we figure out things like the speed of light. And our training data looks like that. In the neural network world, we pretty much have classifiers, embedders, and we also have regression. And they look like this. So deep learning, for the purposes of this talk, is machine learning using deep neural networks, trained typically with gradient descent. Okay, so I'm planting my flag. This is the camp that I'm in. This is what I know how to do. Symbolic logic, I don't know how to do that. So how are we going to take this and do it on graphs? Okay, this is probably the most painful slide to look at. Can we just imagine conceptually a world where we can do this stuff on graphs? What would it look like? All right, we've got our linear regression y equals mx plus c. We have classifiers, and we have embeddings, and we have regression models in neural networks, and they all perform super well. How might it look if we're dealing with graphs? So one popular graph approach is to do a neural network embedding. You might have heard of things like deep walk, node to vec, graph sage, graph convolutional networks. There's a collection of things. A chunk of those, not the convolutional networks, but graph sage, deep walk, node to vec, do walks within the graph. So they take the graph, they do lots of random walks typically on the graph, and then they take those walks and use them as sequences to put into a recurrent neural network. So they turn the graph into a load of sequences, and then sequences are something that we can work with recurrent neural networks. But my contention is this isn't graph native. Okay? Every time we take a random walk in the graph, we lose a load of information. What we want to do is
have something like a regression where we say, let's figure out a model that can convert a graph or a subgraph into a prediction of some property on some node. That's what I want to do. That's the input pattern I want to have. And I'm going to learn some weights on this, and then I'm going to train that either with a graph or with a load of small graphs or a load of subgraphs. And then we can extend that concept, that vision, to classifiers and embedders. And the main difference is with embedding, we're going to expect to have some fixed graph where I learn an embedding of every node and every edge. With these two, I'm not pinned to a fixed pre-existing graph. I'm just learning to interpret individual graphs or subgraphs. Okay? And so I might be able to apply these, I want to apply these, to graphs I haven't seen before. Right? I want to learn how to process a graph that the model hasn't seen before. So, obviously, we aren't the only people who are trying to do this. It's a reasonably obvious idea. So, what's the state of the world at the moment with deep neural networks on graphs? There's a lot of people doing this research in chemistry, and that's interesting, I think, to this community because in chemistry land, we have loads and loads of very small graphs, and we try and learn from lots and lots of small graphs to predict things like what reactions will happen. And there's a lot of research on very big graphs. This is protein-protein interaction data. This is citation data from scientific papers and journals, and this is Reddit. So these are the kind of performances that are state-of-the-art. This is a node categorization task, and this is a predicting chemical reaction task. This is its ability to predict the correct answer the first time. That is its ability to get the correct answer somewhere in the top 5 predictions that it made. So these 70%, these 60%, 50%, 80%, they're not the same level of superhuman accuracy that we see with image classification or natural language. So we can't just take what people are doing already and turn the cog, put different data in it, and expect to get good performance. So one of the challenges is this dimensionality challenge. How do we take our variable graph structures and turn them into a matrix? Because in deep learning with neural networks, everything is a matrix. So somehow we've got to take our graph and shove it into a matrix form. Or we do the kind of cheats like taking random walks. So people say, or I hear people saying that deep learning is good for unstructured data. They say images are unstructured, text is unstructured. We can use deep learning to extract information and structure that data. And they say it's bad at structured data. I've paid some data scientists to try and turn my big tables of data into some kind of useful predictor, and it doesn't work very well, and it costs a lot of money. I contend that that's not true. Actually, deep learning is good at some very specific structured data problems. It's good at sequences, which we use recurrent neural networks for, and it's good at dealing with images, which we use convolutional neural networks for. And these have very specific structures. In image, I know that this node is more relevant to that node than this one. So we know that the proximity in the grid of pixels is more relevant, okay? A nearby pixel is more relevant to a given pixel than a pixel far away. In sequences, we say that this node is more important to this node than that one over there. Okay, so we take adjacency in the sequence, and we walk the sequence, moving along, updating some state. Sometimes we walk it from 2 directions, but we always have that prior knowledge that something that is next to us, adjacent in the sequence, is more important than something that's far away. Okay, what about Go? So Go is even simpler in one way, more complex in another. In Go, every position on the board is equally relevant to every other position on the board. So this dense model works really well for Go, because a move that you make here might have some effect on this square over here. And so saying that this position and this position might have the same weighting on our intermediate state is ideal. With images and sequences, the state-of-the-art solutions don't use plain dense networks. Okay? If we imagine this sequence in that pattern, that would be like saying we take each of these nodes and put them each in the input layer, and then the first hidden layer is some function of all of them. We don't actually do that. We have something that walks along the graph. For images, we use convolutional neural networks. So we don't connect every single pixel in the input layer together in one dense net, we use a convolution kernel. So here we just say, let's just take the pixels that are adjacent to a given pixel, convolve them with some learned weights, and output something into the intermediate layer. So we talk about this concept as being structural priors in our network. So earlier I said we don't pre-program rules of grammar into a language model, but actually we pre-program some kind of concept of how information is related to other information into the models that we use. So the graph deep learning problem is more than just figuring out how to stick a graph into a matrix and then use all of the techniques we already have. Okay? We need to figure out how to retain the relational information that's present in our graphs when we use it in a matrix in a neural network. This pattern doesn't make sense for this graph. Okay? All of these are not equally important to each other. This product is more important to this company than like this node over here. So we want to keep these relational information. If I just stick it in this, all of that information is lost. And the first thing the model has to do is somehow relearn all of that stuff that we forgot. This applies whether we're dealing with transport networks, whether we're dealing with semantic graphs. The same problem applies. We want to keep the information in the graph. So the challenge is not about dimensionality. The challenge is about inductive biases. Okay? How can we structure the neural network to work well on graphs in the same way that we have neural networks that are structured well to work on images and ones that are structured to work well on text or sequences? It turns out there are some people who are cleverer than me who work on this. So you work on anything in this field for a while, and you get used to Google, typically, occasionally Facebook, publishing something that overtakes you in one bound. So I'm going to talk a lot about things that come from this paper. Relational inductive biases, right, and graph networks. So it should be pretty interesting to all of us. Unfortunately, this is how it looks if you read the paper. These are the only equations in this presentation, and that is very much not the norm for anyone talking about deep learning. But this paper presents this concept called graph networks, and they present this algorithm, which they say is a generalization of many, many different graph algorithms. So this is a generalization that includes things that have nothing to do with neural networks. So you can fit PageRank within this algorithm they present, but they propose it as being useful for training graph networks. So the algorithm they propose is, first of all, you take every edge, and you look at the nodes it's connected to, and you update the properties of the edge. Then you take every node, and you look at all of the edges connected to that node, and you update the properties of the node. Then you have some global state. You look at the whole system, all the edges and all the nodes, and you update the global state. And for each of these update steps, you have two equations, and you have two functions. One is an aggregator, and one is a transform. And with these 6 functions, you can plug neural networks in for each of them, and you can train it with gradient descent. So the thing that we think is useful about all of this is we've retained the properties of our graph and the relations in our graph, and at the same time, we've figured out a way that we can do stochastic gradient descent. So instead of trying to stick the graph into a neural network, what we're doing is putting neural networks inside the graph and training with stochastic gradient descent. Okay, so this is a slightly simpler representation of that, in case it was too much. So what we do is we have a graph, we load it into memory, and then we do many iterations of this function where we update the graph based on that algorithm using a load of weights and some controller that we've trained with a neural network, as a neural network. And eventually, after we've done this cycle of updating the graph in memory, reading it out, updating it, we get some output, and hopefully it's the answer. So that's how I think we want to do deep learning on graphs. Does it work? And these are some of the results of our experiments. What we did first is we created a data set. That's pretty typical data science. Right? We created a data set, so now we've got a benchmark to work with. And we made a synthetic data set so that we knew that our models work if we get to 100% accuracy. With real-world data sets, you might get to 95% accuracy, and that might be the best possible, but it's pretty hard to figure out if that's what's going on or not. So we made a synthetic data set modeled on transport networks. And our synthetic data set consists of data points of a graph, a question, and an answer. And each of these graphs is unique. So we train our network not on a single graph, but on different graphs. So it has to learn to use the information in the graph in a single shot. And so there's some stats for our data set we created. Our data set looks like this. So we create, for every single one of those 10,000 points, a unique transport graph that has a few simple heuristic properties. And we choose questions like these. This is a small set. There are 21 questions. So this is a subset of those 21. And these questions require the neural network to do different things over the graph. Okay, it's got to have skills like counting nodes and counting edges as it walks the graph. It needs to be able to pull properties off of nodes and actually properties off of edges. And it has to do some questions that require multi-step reasoning. It can't just read one value out. It has to traverse the graph in some way to answer the question. So to get 100% on this, we need to have a neural network that's trained and can perform all these skills on a graph that it hasn't seen before. So this is where we are at the moment. We're working our way down this list, and so far we get 98, 99% accuracy on these kinds of questions. And at the moment we haven't yet tested these. But in here we've got some which we're pretty proud of. So we've got things like, is there a station with this name? Is there a node with this name? Does this node exist? That is surprisingly hard to do with neural networks because they're often trained to pick the right answer on the assumption that a right answer exists. And training it that there's no right answer is quite hard. How many stations are between station and station? To answer that, it's also found the shortest path. You have to find the shortest path between two stations. And that's Dijkstra's algorithm. And our network has learned how to do Dijkstra's algorithm, and it has learned when to apply it. Because we give all of these questions to network. So it has to know that question requires me to do this algorithm to get the answer and then do the algorithm. So we're pretty proud of that as well, because it's learned that without any prior from us. We haven't given it any hints that would particularly help with that. So we think this works, and DeepMind think this works. So I left that with question marks because we haven't solved all the problems you want to solve, for sure. There's still unanswered questions like the previous slide. But I'm going to talk a bit about how it works. So we've got 5 minutes. This is going to get intense. We've got questions like this, and we've got these data points. DeepMind gave us an algorithm for processing a graph, but we've got this problem where we've got to get from this question, and we've got to get the predicates of this question into the graph. So we need to prime the graph to answer our query, and then we can crank the handle on that DeepMind algorithm and iterate. And then at the end of that, we have to figure out how to pull the answer out and turn it into some useful answer text. So now we've solved this inductive bias challenge with DeepMind's algorithm. Now we have this starting condition challenge. How do we take a specific question and prime the graph to answer that question? Okay, attention is all you need. These guys know what they're doing. So attention is a new building block, or a relatively new building block for neural networks that's different from our densely connected layers. So we've got rid of this, and we have this. What this attention lets us do is it lets us pick over a variable length list of entities, and using some query, we figure out which of these entities are most interesting to us. So that's the idea of attention. And then we aggregate them in some way and output a fixed size signal. So it lets us go from a variable length list to a fixed size signal predicated on some query. And it's differentiable, so we can train it with stochastic gradient descent. So this is how we apply attention to solve that initial problem. We want to prime the graph, and we take our query, and we figure out how to combine our query with this attention cell to update the graph. And based on how much the attention cell cares about each of these nodes, we have an input signal that gets written with different strength. So typically, we'll pick one node that matches very well with the query, and we'll write a strong signal on that node. And so that way, we prime our graph. So it has all the initial properties in it, like the name of the station, how clean the station is, the name of the line it's connected to. But then we add an in-memory value, which is the input signal, which is predicated on the question. Then at the end, okay, we can crank our handle and we think that the algorithm has figured out the answer. We somehow have to read out the answer. So now we do an attention-based read. And we have this list, which is all of the nodes or all of the edges going into our attention. We have the original query again. And we say, which of these nodes looks most like the answer to the question? And we pull it out. And so combining these, we got our attention write and our attention read. And this whole thing is end-to-end differentiable. So we can train on our simple triples, wherever we were, these things, differentiate it end-to-end, and learn how to answer the question. And whatever algorithm is going on in here, the system figures it out, okay? So that's pretty awesome. So what have we found? We've got a deep learning model that can learn how to navigate graph schema. It can learn to do multi-step graph algorithms. We can do end-to-end training on it, okay? So we don't have to teach it about what kinds of relationships we have or anything else like that. It can figure out how it wants to use the relationships. And we can use a single model to solve multiple questions. So a single model can learn multiple algorithms, and it can learn which algorithm to use in a given situation. And we think that this has the potential to be useful in all kinds of situations, right? Assistants like Siri, for legal cases, like understanding legal documents and answering questions. Pretty much any graph problem you think of needs these primitives to solve it. Cool. Thanks very much.
So I see a question there already. Yeah.
If you're dealing with personal data in a graph, you're going to be subject to GDPR, and that means that what you're doing needs to be explainable. So what are you doing about the explainability of this neural networks?
So these, this message passing process here is somewhat explainable. So we can introspect in the same way, if we go all the way back to this. In the same way that this is explainable in that I can look at the intermediate states of the system, and then I can infer what it was doing. So I can say, in the intermediate state, that attention cell that we're talking about, we can see what parts of this image it's interested in. We say, oh, it's interested in that part, it's interested in that part. And we can see what part of the question it's interested in at each step. So we can break it down, and we can kind of look inside, and then we can say, well, this is what it was doing. That's not perfect, and that's dependent on every instance. So we can't say that it always uses this method to answer this question. But for a given situation, we can look inside it and say, well, this appears to be the process that it's undergoing.
So I guess one of the things I'd be really interested in hearing about is how we can take the semantics that are in a graph and try and somehow put that into the priors you're using. Because obviously nodes have types and subtypes, and properties have property types.
Yeah.
Is there a way we can use that within what you're doing rather than just give it more of a kind of input, output, and learn the model?
Yeah.
Is that something that's being looked at?
I'm sure there are people who are looking at it. Our training methods are schema specific, but unfortunately it's not like you say to the graph, a cat is a mammal, and then the graph knows. Instead, you have this brute force process where you like show it that a cat is a mammal a billion times, and then it's like, oh, okay, I figured it out. It would be awesome to do the kind of thing you're describing, where it has kind of ab initio the ability to know from a graph, right? Rather than learning from lots of graphs, the ability to just be like, well, that makes sense. But I'm not aware of anything that does that with neural networks.
Yeah, I was going to ask a similar question. So I didn't really get what is the input and the shape of the graph that you have presented in the clever graph. So
Yeah.
is a question really a question like text and how the graph looks like? So how are the nodes connected? Is there, for instance, an edge like that encodes closeness, or how
Yeah.
are they linked?
So these are our symbol graphs. They're a list of nodes, list of edges, and an adjacency matrix.
Okay.
That's all. And the properties are tokenized, and the question is string. So we have a list of nodes, and the nodes have an array of properties on them. And those properties are just the properties of that node. We don't encode any other statistics. We don't have a value for like number of connections or neighborhood or anything else. It is just what you'd expect to see if you were writing that as to me as like a Neo4j query. So it just has the properties on the node and an adjacency matrix.
So you have different edges. Let's say this station is close to this one, and
No, we just have this station is attached to this edge where the edge is the edge that you'd expect. So there's no relationships other than this connectivity from the transport graph. I don't want people to get too hung up on transport graphs because this is generally applicable. But yeah, in this case, that's the only edge.
Okay, so the edge basically just says these two nodes are somewhat related, but doesn't state how. So this kind of knowledge is lost.
Yeah, so it does have the line. So we'd be like, this is the circle line, this is a district line. And some of the questions require it to traverse specific lines. So it is aware of the different types of edges, and it learns that it has to take the edges into account. But this is simple. We'd like to build ourselves a data set once we finish this one where those kind of relationships and something more semantic logic is involved, so we can really prove that it's able to learn like semantic logic and which edges it can traverse in what order.
Yeah, another question. If you're dealing with, I don't know, criminals or bad guys or whatever, you may have a relationship that has a percentage probability. Can you handle that sort of issue as well?
I'd expect to be able to, because the way that neural networks are very good at handling probabilities in general. That's often the way they're trained. So things like word2vec is trained to predict a probability distribution. But I've got no evidence that we can do it in this example.
Okay, let's take one final question.
So the paper that you pulled up in the wax vertical now,
Yeah.
was Google and University of Edinburgh.
Mm-hmm.
Is Edinburgh the leading, the thought leader in this work, or Google the thought leaders in this work? I mean,
So
where do you see the innovation coming?
yeah, in my experience, the innovation is oriented around companies, not universities. But here the lines are incredibly blurred. So there are plenty of people who hold positions, a senior position in an organization like Google or Facebook, and also hold a senior position in a university like the University of Montreal or the University of Edinburgh. And things that come out tend to be like that. So you've got people from the University of here and people from this organization.
So collaborative research.
Yeah.
Okay, that's it. Thanks a lot, Andy.